Should we start now? Okay. Bindong, okay.
Yeah,
okay.
Sure.
Hi, everyone. Good day. I'm very pleased today to have Professor Bindong from University of Beijing to give us a talk. Professor Dong got his PhD from University of California at Los Angeles. And then after that, he was a visiting assistant professor at UC San Diego. And then tenure track professor at the University of Arizona. He moved back to Beijing in 2014 to the Beijing University. And now he's the director of the Center for Theory of AI in Beijing University. Professor Dong works in mathematical modeling and computations in imaging and data science. Especially, he's always trying to bridge the wavelet theory and nonlinear PDE. But recently, he tried to bridge differential equation and optimal control with deep learning. And today's talk is exactly on this topic. So he would be talking about deep CT imaging by UnRolled Dynamics. So Professor Dong. Oh, by the way, so if you have, if all our participant has any questions, you please wait until the end of the talk and then push the raise hand button. We will unmute you and then you can ask the question to the speaker directly. Okay, Bin. Yeah.
Okay, all right. Thanks for the introduction. Also, thanks for the invitation. Thanks to all the organizers to give me this opportunity to present some of our recent work on this topic. Actually, I look at the list and actually I watch a lot of talks of the seminar, really high quality talks on YouTube. And some of them are actually quite related to what I'm going to talk about today, like a talk given by Professor Jin-Kun Su, Rebecca Willett, and Unita Elder. I think you will see some overlaps, but I will present some of our recent work that's quite interesting, but it's still at its very preliminary stage. So I'm very open and appreciate comments and suggestions. So trying to go to the next page. Okay, so this is the outline. I'll discuss very briefly on the mathematical modeling. Just a very quick review for those who are not quite familiar with the background, and then discuss how we view, actually not just us, it's actually a very, a pretty sizable group of people are actually looking at deep learning through the perspective of optimal control. And actually we just had a very nice mini symposium of, MDS, Mathematical Data Science, organized by Lars Rafaldo and his colleagues. And, basically we regard deep learning as optimal control, and we can do a lot of modeling and design new algorithms through this perspective, and the focus of this talk will be will be the UnRolled Dynamics, and how do we do CT imaging, and how do we design reconstruction models and algorithms, and also how do we improve scanning strategy using reinforcement learning. So basically, I'll put everything in the perspective of optimal control, but I will mainly focus on CT imaging. But of course, the techniques can be generalized to other imaging modalities. But of course, you need some other changes. But the modeling philosophy can be applied to a pretty general class of U-post inverse problems. Okay, so while CT imaging, I think mathematics plays a very important role in CT imaging. For example, read-on transform, and we can interpret it as an inverse problem. We can approximate using a linear inverse problem, and there are a lot of very interesting, in both theoretical and the practical work has been done ever since the Nobel Prize of this technology. And let me just put this in a more general, image reconstruction framework, where the F is the data that we collect, for example, the cytogram for CT, and A is the projection, is the forward problem, and we approximate the actual forward problem using a linear, using read-on transform, and we want to reconstruct U, and we have additive noise, typically Poisson, but sometimes we assume it's Gaussian. If you look at the past about 30 years, and you can classify the reconstruction methods in this general two categories. The one is versional or optimization models, where we design a function or a functional where you try to minimize it, and you want to find the minimizer of that functional, and that's will be a good solution to your imaging problem. And also you can design PDEs. Not necessarily have a variational model corresponding to it, or iterative algorithm. It may not exactly solve a certain optimization problem, but you can design them based on intuitions or geometric insights, and that in the end, iterative in the end, that give you some good results. So the typical variation models that have these two parts, regularization and the fidelity, and a lot of the designs oriented around finding a good regularization are such as total variation, wavelets, and many others. Total general variation, low rank, non-local means, and etc. Okay. And now many people are using deep learning. They either train a generative model or other a very complicated nonlinear neural network to represent this sparsifying transformation that we typically use in the past. And for PDEs, also many very successful examples, such as the paradigmatic shock filters, and also Bikert. I think he has quite a few very interesting anisotropic diffusions that does pretty well for image restoration problems. And also iterative wavelet shrinkage. I think the very first wavelet, well, at least one of the very first wavelet algorithm is actually iterative in nature. And later was proved that it actually minimized some objective function. Okay, but in terms of design, it does not necessarily does that. So all of this, we actually we had a review paper that actually summarized all of this from a data-driven perspective, and also I've done some work trying to show theoretically justify the relations between PDEs and iterative wavelets shrinkage, and also the wavelet based regularization, and also the TV based regularization. There are some very interesting connections between them, but I will not go into that. So if we look at the development, this is my own perspective. The development from just a chronicle order. So around 90, most of the models are handcrafted. That means actually we design it, using mathematical principles or using just some theoretical designs, and variational and also applied harmonic analysis approaches. They fall into this category. And around the 1999, around 2000, we start to see a hybrid of handcraft and data-driven. A typical example is method direction and also KSVD, where we actually learn a dictionary. We design most, but we let the data to decide on a few of the parameters. Okay? And also statistical models actually falls into this category, of course. And in 2012, we see a big wave, a big rise of deep learning, and a lot of it actually replaced a lot of original methods, and it's the state of art for a lot of tasks in computer vision and also in many other fields. I think this is if you think about what's actually changing. When I was a PhD student at UCLA, that's from 2005 to 2009, when I have a data set that has maybe 20 or 50 medical images, that's pretty big data set. And we do not really have just millions of images. And even I had millions of images, I don't know how to actually compute or process them. So I think what's changed is that now we have more and more data available, and we have more and more processors. At least for me, that the processors are actually getting cheaper, and it's easier to get access to GPUs, and so that you can really just leverage the large data set and do some computations and rely a little bit more on learning than what we did in the past. Okay, so that's what's changing. So deep learning has been a great success. But also, there are a lot of drawbacks of deep learning. I think you must have heard a lot of just drawbacks of deep learning, and that's why we have this theory in AI, which mostly working on just laying the theoretical foundations for deep learning, and also for reinforced learning and AI in general. So what we want to do, the two things that our group are particularly interested in is, the first one is theoretical guidance. So we emphasize on guidance is because, well, it's already pretty difficult, to have a theory for deep learning. There are many theories, but what's more challenging is that to really actually guide applications based on theory. So we have there are not many examples that theory can really guide applications, but there's still a lot of work need to be done, and also interpretability and robustness. This is actually we didn't have all these problems, when we use variational or apply harmonic analysis models. We have pretty good theory, and it's fully interpretable, and we can show that it's quite robust. But now we have all these issues for deep models. So how do we need a way to look at this deep neural networks or deep learning, and from a perspective that we know, we are actually quite familiar in mathematics, and our perspective, and as like I said, as well as many people in the world, think of deep neural network as some kind of dynamics. And the learning of it, the training of it, is optimal control, where you actually try to control the parameters, and so that you minimize a certain energy or maximize certain reward. Okay, this is not actually new. Actually, I look at the history and I found that Nobel winner, he had a book, actually had two books talking about cybernetics. He coined the term cybernetics, which means control. And it pretty much describes what a intelligent living organism should possess. Okay, the great sensing. Okay, so that you know your current state, and also the control of your parts. Basically, you can navigate or you can move if the environment is not in your favor. Okay. So this basically describes a reinforcement learning type of, but it is control. Reinforcement learning, can be cast into this control framework as well. And some people, says that, well, the cybernetics pretty much lay the foundations of neuroscience, AI, and also the modern version of optimal control. Okay. But I think the modern renaissance of optimal control, I think, started by the work of Wei-Nan Yi, Qianqiao Li, and this group, and also Lars Ruthotto and Alda Haber. They studied this deep network. It's a very successful deep network called ResNet, and they show that actually it is this bypass is a forward Euler discretization of a dynamic system, so that the training of ResNet can be cast into this optimal control. So I just write it in a slightly more general format. Let me change this marker. Okay, I don't think I have that option. Okay. Anyway, we later show that if your network has some certain randomness, for example, stochastic depth or shake, actually it is, you can show, for some example, you can show that it weakly converges to this SDE, and so that you can think of it as a stochastic control. Okay. And then also, if you choose different discretizations of this dynamics, you end up with different architectures. And we have one example in our paper in SML 2018 that it does a better job than the ResNet. Okay? And there are many other designs as well. Okay. And also, if this dynamics is a optimization algorithm, or it's an iterative algorithm, in particular, it could be a optimization algorithm. You can do end-to-end training to determine the control parameters, for example, some hyperparameters in your dynamics, and so that a certain your loss function is minimized. Okay, you have this running cost and you have this terminal cost. Depending on your task, you may have both, or you may have just the terminal cost. Okay, and what Gregor and Lacan, they first showed that, well, you can actually speed up optimization by choosing a perfect set of hyperparameters for a given set of data. And also later, several other group of people show that you can actually use this to design better architectures just feed-forward networks that can do some tasks pretty well. Okay, and also, oh, I think there's a very nice review written by Liu and Theodoro. It's the control perspective for deep learning. Okay, and also if your dynamics is a PDE, well, the discrete version of it will give you architectures, and this control parameters omega could be the discretizations of PDE if you want to use deep learning to solve PDEs, or it could be the parameters that determines the expressions of your PDE. Well, that means it's an inverse problem. So you can do either inverse problems, and also you can solve PDEs as well. Okay, and you can also put this into this PD framework, and you can explain many interesting architectures. For example, you can understand that dropout actually leads to a specific form of this of the Laplacian term, and that actually leads to certain smoothness or robustness. Okay, and you can do many other things as well. So I'll just skip this. And with this control perspective, you can actually explain supervised learning, not only supervised learning but also reinforced learning and also meta learning. So I just rewrite this dynamics a little bit. The control parameter is U, but actually it's depend on it could depend on some parameters theta as well. So if U is your control, this is a typical supervised learning control. Okay. I'm talking about the model, not the training yet. And if U, this U depends on some parameter theta, but also depends on the current state of xt. Well, this is the reinforced learning type of control. Okay, and if your control U depend on the variable theta, and it could be it takes some other general forms. This is the typical meta control. Basically, the meta learning is that the control parameters is also parameterized by some other parameters theta. Okay, and in terms of training, we basically have a BP or PMP. This just directly taking derivative or look at the KKT of this optimization problem, or you lift it in the higher dimension and look at the value function, the HAB, Hamilton-Bellman equation, and then use dynamic programming to solve it. And what we often see is that people use BP or PMP to solve meta and supervised learning control, and then people use dynamic programming to solve reinforced learning control, and there's some crossovers as well. Okay. All right, so basically you can put a lot of learning mechanism in this control perspective. And now what do we do with it? And the reason that we really like this perspective is it make it easier for us, at least on a higher level, to actually combine the traditional wisdom that we had in designing iterative algorithms to solve imaging problems, and with the deep learning. Okay, but the trick is how which part that we should adopt the handcraft model and which part we should actually use machine learning to learn. So this is actually there's no general guiding principles, but we have a lot of experience. The community actually has a lot of experiences on that. So what I'm going to show you in the next few in the rest of the slides is basically following such perspective. Okay. So the very first group of work that I'm going to show is the Aerodynamics. Oh, this is the work done by with my postdoc Hai Miao Zhang, and also my colleague Baodong Liu and Hengyun Yu. They are actually medical physicists. They're working more familiar with the machines, and we're designing the algorithms. So a little bit more a review on the Gregor and Lacan's aerodynamics. So they started with this iterative self-thresholding algorithm. If you write the computation graph, it looks like this, and you can actually unroll it, or if you do not want, you don't have to unroll it. This is an RNN type of network. And if you have a lot of input X and also the actual code Z, if you have a lot of these pairs, you can actually train, and so that you can determine the hyperparameters in this network, in this ISTA. Okay, they call this learned ISTA lista, and they compare it with the FISTA, which is the speed up version, and they show that it's actually faster. Okay, at least with 7 iterations, it achieves a smaller error rate. Okay. Other than the optimization algorithm, you can also unroll a discrete version of diffusion. This is a very nice work done by Chen Yu and Park in 2015. Actually, they discovered this residual structure earlier than Kaiming He. But they did the denoising problem. If they did their image recognition problems, it will be this work that actually proposed the residual network. Okay, so I like this work very much. So they started with a nonlinear diffusion, and they used forward Euler to discretize the time, and they replaced the discrete forms of the convolutional operators by just convolutions with these kernels, and they just train these kernels and also these hyperparameters so that this network does denoising, and it does denoising better than the previous SOTA like BM3D and the WN and M, etc. Okay. And of course, if you unroll a more sophisticated optimization algorithm, starting from a more sophisticated optimization model, and you choose this is interesting. This is a optimization algorithm that we rarely use in practice. We normally just use ADMM so that each subproblem is easy to solve or has a closed form solution. Okay, that's actually the point of doing this divide and conquer business. But they actually show that if you use this, it actually generalizes better. So it's a big a mystery to me that why you use this to inspire a network that generalizes better than use the actual ADMM. Okay, this is what they show in their second paper. That in their first paper they really use ADMM. They cannot really beat BM3D, but in their TMI paper, I think this appeared in TMI. They can actually beat BM3D with this specific architecture. Okay, and this is what we did is that we use a even more carefully designed variational models, okay, optimization model, and use ADMM and did a little bit change on the design of the loss function, and so that we can achieve even better results, better than the previous state of art. So I would not bore you with the PSNRs at this moment, but this is actually you can see that the unrolled dynamics can get infinitely more complicated. But of course the question is so in this, for example, in this model, actually we actually use a neural network to approximate the inverse, which is also what the primal DUNet did. Okay, and this the sparse limit transformations are actually learned, and the hyperparameters are learned, and also the proximal operator or L1, this thresholding operator is actually also learned. But then we start to ask ourselves, do we really have to learn this many parameters, and are these actually essential to learn all that? So we in our recent paper we did a little bit. It's just a very brief summary. This is hardly from complete list. We just choose those that we're quite familiar with. So a typical image reconstruction algorithm that looks like this: you have your approximation for U and your sparsifying step that extracts the sparse codes of your U, and then you update your residual, and then you just iterate. And if you look at the existing methods, they all use different ways to they actually replace different components of this UZ sub steps by using deep networks, and they all have a lot of just training parameters. Some of them just replace like PDNet, they replace this U and Z step entirely by CNN, and also the image prior, the W transform, the transform sparsifying transform is also learned. Okay, but what we propose actually is that you don't have to learn all that. You can stick with your soft thresholding, and you can use your just handcrafted transform. And for me, I'm a wavelet guy. I use the wavelet frames, just piecewise linear wavelet frames, and you manually just fix lambda and gamma, and we only learn just a part of the in the U step. So I'm going to show you exactly what we did. So we started with this HQS. It's a very intuitive variation model. This is the fidelity, and also this two combines to give you the regularization. Okay, U needs to be sparse under the transformation W, and you can do alternative optimization. You solve a U step and you solve a z step. Okay, the z is precisely the wave, the thresholded version of the wave, the sparsified version of the wave transform of U. Okay, and this inverse, since we're doing CT, remember we're doing CT, so we use just a few steps. For example, 5 steps of conjugate gradient. And what we design is that this iterative scheme is the backbone network, and the only just component of it we need to be learned, that we want it to be learned from the data, is the initialization of this conjugate gradient. Actually, when we use this iterative algorithm to solve CT imaging, the initialization actually just at the beginning we just fix some random initialization or just some very rough reconstruction, and during the iteration we just use the previous approximation as the initialization of the conjugate gradient method. Okay, it's very straightforward. We never thought that whether this is optimal or whether we should actually change that. But interesting that we show that if you use a convolutional network, a CNN, it could be a vanilla CNN or it could be a more sophisticated version, a heavy-duty version of CNN like a UNet. And this CNN determines how to initialize your conjugate gradient at each step, judging from the current approximation of the solution. So it takes in the solution and then and the inference on the initialization of the conjugate gradient. But that's the only part that we learned, and everything else is actually fixed. Okay, so if you actually use the vanilla version, we call it a low. That means it's a light version of it. You have much fewer parameters than the previous designs. Okay, but of course, if you use a heavy-duty version, it has even more. So this is a factor of 10. It's a factor of 10 less parameter. This is a factor of 10 more parameters. But if you compare the data dependence, actually the specific design, the reason that we call it meta is because this is a hypernet design. Okay, and that's a special example of meta learning or the meta network. Okay, if we train that we train it on AAPM data, but if we only use 1% of the training data, both of this meta nets, regardless whether it's light or heavy, it does better than the previous versions. Okay, and of course, in particular, this light version, does better when we have fewer parameters. Okay, so this is the light version, and this is the heavy-duty version. Okay, this is not surprised that we have a lot of parameters, but it does not affect so much comparing to this PDNet or the GSRNet because of this hypernetwork design. Okay, so you can think it this way: if we do a very lousy job on guessing what's the best initialization can be, but this backbone network can still work very well, because what we did is just choose some random. You can choose some random initialization. This will still work. So that's why it's not really very sensitive in bad options or bad choices of the CN. But if it does a good job in inferencing on the good initialization, it can significantly improve the results. So that's what I'm going to show you in this big table. One thing I need to mention, that we actually trained with 180 angles, and we assume that the noise additive Gaussian with the noise level 0.05. Okay, so this is the training setting, and what you show here, this is all generalization. So it's on AAPM. We train on AAPM. Okay, so we look at the performance on AAPM, but with the higher noise levels. With 180 is the training angle, but the 120, 90, and 60 are actually outside the training setting. Okay, and also we test everything on another data set without training. So we just train it under this specific setting, and we do generalization on that. And you can see that in average, in general, this meta version outperforms the traditional and also the classical and also other deep networks. And what at the extreme cases, the heavy duty version is still the best, but the second to the best is no longer the deep version. It's actually the traditional algorithm. Okay, we know for the models that we design, handcraft models, they do not have this generalization issue. Okay, well, the only painful part is to tune the hyperparameters for different cases, but other than that, there's no generalization issues. But for deep models, especially the non-meta version, just the straightforward supervised learning methods, they do have this, to different extent, they do have this generalization issues. So let me just quickly summarize that we can actually generalize to different numbers of views, to different data set, to different noise levels. And also it can generalize to different noise types. Remember that we trained on Gaussian with a noise level 0.05, but we also tested on Poisson with different number of views. And you can see that the meta version also generalizes pretty well, okay? So it outperforms the traditional method and also generalizes better than supervised learning model for the supervised learning models. Okay. All right, and this is some visual comparisons. So I will not bore you with the images, but if you look at the residual, it's pretty clear that this, especially this heavy-duty version, it does pretty well. Okay. And this is actually the real data. We try to generalize on this real data, and you compared it, you can see that it also generalized. Well, it's not that good, but I think it's quite okay. On real data for different number of views. Okay, so this is data provided by Professor Heng Yu from his lab. Okay. And also we did a little abolition studies because let me just go back a little bit to this network. Okay, because what we did in the past is that we tried to learn a lot of things in these backbone networks. For example, it's at least at first I thought it's a little bit counterintuitive why why learning the sparsifying transformation W may not be helpful. How can we actually just fix the sparsifying transformation? It still does a good job. And also these hyperparameters, we know that they're actually quite important for different data sets. But it turns out that actually this deriving a good initialization for CG actually compensated for all of those. So now the natural question is, so what if I also learned the sparsifying transformation, also these hyperparameters lambda and gamma, and look at the different combinations, and is this actually the best option? Okay. So we did a quite exhaustive experiments, and to show that for different scenarios, and we're learning just the CG initialization, or learning just the sparsing transformation, or learning just the hyperparameters, or the combinations of those. So in average, you can see clearly that learning just the the CG initialization actually does better. And I think this is particularly because this is all generalization scenarios. So it actually does better in general. So I'm not saying that this is true in general. I can only say that it's probably true for CT and for the specific setting that we're actually tested. If you use if you unroll another dynamics for other imaging, this may change. So I'm not saying that this is universal. There's no proof. This is only empirical, but it's actually interesting. At least it's quite surprising to me at first. Okay, so we just need to learn the initialization of country gradient. Okay, and what actually this does. So you may say that, okay, maybe this CAN, especially when you use UNet, it's so powerful that actually already does image reconstruction. So then you do not really need this backbone network. But what we actually show is that it's not the case. It actually supports the backbone network to do better reconstruction. So what we presented is that, okay, so this is the structure similarity and also the PSNR of the this U00, which is the initialization of the CG in the very first layer. Okay, and after a few steps of country gradient, we arrive at a better results. And if you continue, okay, this the UNet, the CN here actually derives a better and better reconstruction. So we just compare U and the actual image, and you see that the quality improves. And also alongside of it, the country gradient, also the backbone network actually improves, polishes, the coarse reconstructions that are actually derived by your networks, okay, and so on and so forth. So this actually shows that these two networks actually helping with each other, and you cannot just rely on this to do the job. Okay, you have to have this both mechanism. Okay, So this is actually not a very recent work. Some of you may heard me talking about it in some other occasions, but I really like this work. So what we did in image-based diagnosis or recognitions is that we treat image reconstruction and abnormality detection as two separate steps. Okay, and we measure image quality based on PSR, which is what we did in the previous few slides. But the problems of this two-step approach is that the raw data actually has more information. If you reconstruct image and lose some information, and you do abnormality detections, and that lost information can can never be recovered. And also, a good quality metric needs to be task dependent. Okay, we use PSNR because we're not really thinking about how we're going to use these images. But if we know exactly what we're actually interested in these images, then the quality metric need to be you need to be adjusted according to the task. So can we make it end to end, and also does it help? So that means we want to remove this barrier. And with this Unreal dynamics, it's very easy to put two pieces together. So we have this Unreal, you can pick any Unreal dynamics that you like as your image reconstruction, or just an iterative algorithm, without any trainable parameters, and you combine it with your favorite image recognition network, okay? And you can pre-train each of them, and then you connect them, and then you do a fine tuning. So what this actually does is that first of all, it can improve recognition, and for this specific test, it can actually improve false positive. This is a long nodule detection data set from AAPM. Okay, and what's more interesting is that this later part actually gives you a task-dependent image quality metric. Okay, so what do I mean by that? If you compare it with two-step approach, that is, you use a deep method to do image reconstruction and also a deep method to do recognition. So basically, the image that you reconstructed is smooth everywhere because your reconstructor does not know how you're going to use these images, so it just created a very smooth image everywhere. But if you do it end to end, you can see that it does a better job in regularizing the image inside the long region, but it doesn't really do much outside because this is nodule detection. The task doesn't really require you to have a clear image outside the long region. So it actually automatically give you a task dependent, just reconstruction or a quality metric. So it tells you that we do not really need to do a good job outside the long region, but we need to do a better job than, for example, figure back projection, within the long region. Okay, that's actually quite interesting. And actually, this idea was also actually proposed earlier by a group of people on medical physics, but they actually argue that we need to look at the raw radiomics. That means we need to start from raw data and then do the radiomics business. Okay, but this paper is a discussion paper. They didn't actually tell us exactly how we should achieve this, but they just show that to achieve radiomics is actually very, very important, from medical physics point or from a clinical point of view. And also in computer vision, Thomas Huang's group actually did work. They call that just connecting the low-level vision with higher-level image recognition. Basically shows that when we do image reconstruction, we really need to think about the task, the downstream task that we're interested in. Okay, so this is an independent and separate work that's done by people from computer vision. Okay, so this is the last topic. And so in the previous, all the previous reconstructions, we pretty much fixed. This is one of our very recent work we submitted to NeurIPS, but I don't know whether NeurIPS would appreciate a medical paper, but it's an application of reinforcement learning. So all of the previous model that I talked about pretty much has a fixed A. So the imaging, the scanning, or the sampling, okay, either in the either the stenogram or your sampling in the case space for MRI, okay, or other sampling, it's actually fixed, and this A is actually fixed, and the designer are actually designing a better regularization or using a better sparse transformation or whatever models, but this A is fixed. But can we actually select A adaptive to F? That means, so we use the term personalized CT scanning. That means for a given patient, we want to design we want a way to automatically generate a good scanning for this specific patient. Okay, so we know that in general, just equal angle scanning or random scanning, we know from computer sensing that it actually does a good job in average, or in general, it does a good job. But for a specific patient, it cannot be optimal. Well, maybe it's optimal, but it's most likely not optimal. But can we actually achieve that? It turns out that quite a few people discuss of how to actually improve the scanning strategy. For example, static scanning or dynamic scanning, or some of them actually use a deep network to learn some value function, and given that value function, we can roughly know which angle that we should take a measurement for CT. Okay, at which angle that we that most likely greatly reduce the distortions in the reconstructed image. Okay, it's sort of related to active learning, but not quite. Okay. And I think about it that what we want to do is actually, for a given patient, we want to know exactly how many angles and which angles that we choose. And also at each given angle, what's the dose that you need to inflict on the patient. And so that the total dose, we want to control the total dose. So basically what we want to optimize is that for each given patient, we need to know how many angles and which angles we should take. And for each given angle, how do we allocate the dose? So that we can maximize the image quality while we can restrict the total amount of dose for each patient to a certain amount. Okay, and to do that, especially the angle part, it's actually a combinatoric optimization, and people actually use reinforced learning for combinatoric optimization problems in the past. Like I think this is Google's work. They use reinforced learning for travel salesman problems, and also you can use that for vehicle routing problems, and also for influence maximization problems, and etc. And more recently, I think Jeffrey Ed, he has it's also very interesting work using reinforced learning for STEM imaging. Okay, and if you're interested, you can actually look at the way Jeffrey did in his work. All right, so how do we actually achieve personalized CT scanning? So basically, we regard this sequential, just scanning. So okay, so basically, the scanning is that we need to determine altogether, the number of angles, and also which angles that we need to take. But we think this as a sequential decision making. And so that we use, we formulate this sequential decision making as MTP. So what's this sequential decision making? So at each given state, S1 and ST are actually the projections that we have already took, and also the dose for each given given angles, and also the remaining dose. So this is the state, okay, and the action is we need to determine at next step which angle we should choose, and what's the dose that we should allocate on this particular angle. And we choose this angle among this, from 0 to 179 degrees. Okay, and the reward is actually the PSNR increase. And when we evaluate the PSNR, so actually the state we choose is the projection. This is to make sure that when we do inferencing, we don't have to do image reconstruction. Okay, we only do image reconstruction using SART. We use SART because it's fast. When you evaluate this, the reward. Okay, and the transition is very simple. Okay, so the trade-off here is that if you use a lot of angles, then the dose for each angle will be low, so that the noise level will be high. Okay, if you use fewer angles, then you do not have enough equations, even though the noise is low. So there's a trade-off. So we want to use the reinforced learning, to help us to decide how to choose a better trade-off. Okay, so this is the policy network. It's an RN structure because of the state actually increases along with time. So this is a pretty standard setting. I think similar to what Google did, for this travel salesman problem. Okay, I will not bore you with the details, but basically this network outputs two values. The one is actually the angle. Okay, the one is actually the dose that you should allocate on that angle. Okay. All right. So during training we use SART as reconstruction, but we also tested whether this scanning strategy chosen using reinforcement learning. Okay, this is reinforcement learning. This is dynamic sampling, and this is random sampling. Okay, and this is adaptive dose, and all of these are actually equal dose. Okay, we want to see that the RL based scanning, whether it's actually compatible with other reconstructions, and especially if you use a deep model as a reconstruction, whether we do not really need a smart scanning. What this actually shows that it does generalize to other type of method, and also for each given reconstruction method, the RL based the scanning strategy always improves the PSMR. And even you use a more sophisticated, deep model as reconstruction, it still improves. So that means a smart scanning and also a smart reconstruction, they can really go together. Okay, you can design them in parallel. It's not like you have one that's really powerful, you do not really need the rest. It's not the case. So you put both together, you can have a really powerful reconstruction, reconstruction method. And these are just some visual comparisons. You can see that this reinforced learning will actually lead to better structure. Okay, visually better structure in both bones and also some of the soft tissues. Okay. And if you ask whether it's really achieved personalized scanning, so we trained it on AEPM data with 250, training with 250 images, 2D images, and we tested on 350, images, and these are actually the number of angles selected by the reinforced learning. Okay, this is a distribution of the angles selected, and it's ranging from 45 to 64, I think, and for each given, so for the number of angle 45, 54, and 64, there are multiple examples that it actually chose 45, 54, and 64 angles. And these are the dose distributions, okay? So for the same angle, the dose distributions are similar, but not exactly the same. But for different number of angles, of course, the dose distributions are quite different. And if you look at the images that actually chose 45, 54, and 64 angles, and you can see that actually images with less structure, comparably less structure, requires less angles, but the ones with more structures, it actually requires slightly more angles. It actually makes sense. Okay, it's really does some personalized. I don't know whether this is really optimal, but it's better than dynamic sampling and also than random sampling. Okay, and this is a comparison between reinforced learning based sampling and also dynamic sampling, and these are actually the first 20 angles that he actually selected, and also this are actually the dose. It adds totally to 100. That means it's 100%. Okay, this is 2.4%, 1.7%. Okay, and for dynamic sampling, it's all equal dose. Okay, and it's actually for dynamic sampling, it's also adjust its selections for different images, but you need to preset the number of angles. Okay, and also you do not know how to allocate the dose. You have to average them. But for reinforcement learning, the number of angles and how to choose those angles and how to allocate those are actually determined automatically once you train your AI agent. Okay, so let me just summarize. It's only 15 minutes. Let me quickly summarize. So basically, we look at deep learning as optimal control, and with this perspective, we can easily combine the traditional modeling wisdom with machine learning or with deep learning, reinforcement learning. A lot of interesting techniques in AI in general, can be combined with our traditional wisdom. And for unrolled dynamics is one specific. I really like this approach. But of course, the question is which component needs to be learned and which does not. And I do not have an answer to that. It's just some empirical studies. And hopefully we can derive some, we can go from heuristic to theoretical, and so that we can actually, prove a priori that maybe this part does not need to be learned, and we can just use the traditional design. It's good enough, and for the rest of the part, we really need to learn from the data. Okay, so let me just finish my talk. This is a picture that I stole from David Whipps. if you really like having coffee in the morning, I really like coffee with Coffee Mate. So the Coffee Mate is deep learning, and the conventional algorithm is the coffee in black. You don't drink your coffee like this. You really need to give a really good stir, and so that you can really enjoy the big cup of Joe in the morning. So I'll conclude my talk and open to any questions. Thank you.
Okay, thank you, Dong, for this very insightful and interesting talk. So any questions? Not sure whether I can see the oh yeah, so I can now. Xiaochuan, yeah. So well, I don't know if I can unmute you. Maybe Fidel, you can help. I can. Let me see. So how I can unmute you?
Can you hear me now?
Yeah, we can hear you.
Oh, okay, good.
Great. Yeah,
Please
this
go ahead.
it's great to be at the webinar meeting since March, so it's very interesting. I have a couple questions. I mean, it's just in general. So, thank you for giving the talk. First of all, Dean. You mentioned that deep learning has a great success in city reconstruction. I don't know where the evidence is in terms of success. Can you?
Okay, so I can answer that. I didn't say it's successful in CT image reconstruction. I say that it's successful in quite several tasks in computer vision, natural language processes,
All right.
but not exactly in CT imaging.
All right,
So,
that's fine. So they clarify that. All right.
Yeah.
So when you talk about CT reconstruction, you have a couple examples. Without getting into details, there's a image model H matrix. So how do you define that? What is the specific H matrix you are inverting? Are you inverting that? Any model you talk about like a HF plus noise. So what is the edge? Because when you're actually doing it, the edge can be very, can vary, depends on what model or how you calculate it.
You mean this P?
Yeah, let's say P.
Yeah, this is approximate using radon transform or just
yeah, but it's not radon transform though. When you do discrete, then you have to discretize it. It's a matrix. How you discretize it, it matters a lot. Right. Especially when the number of views is reduced, when the data, the amount of data is reduced. So it matters tremendously. So what is the specific matrix you're using right in your example?
I think it's implemented using Seedance algorithm.
Okay. Yeah. Good. Yeah, the reason I raise this kind of question is that those seems to be a kind of details, but they matters.
Yeah.
Another thing is that I don't know if you're talking about reconstruction. You keep talking about optimal, good enough, all those things. I don't know what that means exactly. For example, in the later part, you say we're gonna of course people are using in industry in product, commercial product, they already have scanners that can change the illumination profiles from view to view. They are doing that already. That's product.
Yeah.
And there's a metric in terms of optimize those things. You use optimal. So out of here, what is the optimal, metric, optimal thing you're talking about specifically?
I think the real answer, I think the really optimal needs to be task dependent. This is what we're actually doing is we're not just at PSRs. We should really look at what you want to do with the images.
Right.
So,
okay.
Yeah.
But here you're saying that you are trying to optimize the illuminations, from view to view or number of views, all those things. What is the metric you're talking about here?
The metric is the reward, the PSNR gain.
Okay.
Yeah.
All right. Yeah, I just want to clarify.
Yeah.
Those things.
Sorry, yeah. So, but what I really think that this should be you should really stick a recognition or whatever n task that you want as your metric here, rather than this PSR. But we haven't.
Yeah.
We're working on it, but we haven't done it yet.
Yeah, that's exactly what I'm asking. This kind of questions.
Right.
Yeah.
Okay. Thank you. So
Thank you.
now, so Xiaoshen, you finish or?
Yeah,
you have...
I'm done. There are a lot of things we can talk about in the future, but I'm done for this now.
Okay, thank you. Well, we have another question from Guoxi Dong. So you can speak now. Yeah.
Yes. So thanks, Bin, for this wonderful talk. And I would like to ask, would you comment on this, what you mentioned in the beginning, that deep learning can be somehow equivalent to optimal control problem?
Oh, okay. Yeah, sorry, I really didn't spend too much time on that because I want to move to the imaging part.
Yes.
Right. So maybe this. Okay. So well, it's this dynamics. If you discretize it, it will give you all kinds of different feed-forward architectures. And in our paper, we actually show that some of the known architectures are different discretizations of this dynamics. So how to understand this? So this X is the input data, and it passes through this, it evolves through this dynamics. That means it passes through this deep networks. And in the end, you have this your output layer, and then you have your cross entropy, with your label, and this is the weight decay, for example, right? Or you don't really have this sometimes. And for reinforcement learning, you really need to have this running cost. So if your network has some randomness in it, and you will have this type of, but it may not be as clean as this version. It could be more complicated, but this is more of a formal a description of optimal control and deep learning. And you want to see a more rigorous version of it, you can read this review. I really like the review that we wrote. Yeah, it's pretty concise and thorough. Yeah.
So this means the network somehow has infinite length.
Well, actually,
has infinite number of lengths, deep layers, something like.
The time is from 0 to 1, and you discretize it using a finite number of steps. So it's finite, but yeah, if it's infinite, it's really hard to train. Even for reinforcement learning, even for dynamic programming, you cannot really train a maybe 10,000 deep. Yeah.
Okay. Yeah.
Okay. So
yeah. Okay. So, yeah.
So you have other questions or?
Yes. So
please go on. Please go on.
So it means this is a when you train the neural network, it's kind of you're solving the optimal control problem, or?
You can think it this way, yeah. Or at least we'd like to think it this way.
Yeah.
Okay.
Some machine learning people does not really. That's why I actually made this little plot to show that when you have this is actually a 50-layer ResNet made by my student Pengfei Jin from Peking University. You have initially you have this 2 data set that's entangled, and after training you result in a vector field. We share the coefficients. You result in this vector field that actually disentangle this data. And in the end, that's why in the end that you use a linear classifier. It does a pretty good job in the classification. So deep network really has this. The very first part is to learn a complicated just feature extraction or dimensionality reduction. And in the end, you just need to do a very simple classification. Yeah.
Yeah. Thank you.
Okay. So do we have any other questions? Seems that we don't have any questions. So if not, then let's. Well, thank you for the Bin for this very interesting talk. So we will meet next week again. The next speaker will be Professor Zhong Yi from KAIST in Korea, in South Korea. So see you next time. Thank you. Bye bye. Thank you, Dong.